Project 8, where we'll be talking about complex numbers. In math, there's a few things that we can't really calculate. One of those things would be the square root of a negative. If I'm looking at the square root of a number like 16, I'm saying what two numbers multiply together to give you 16, and that would be 4, because 4 times 4 equals 16. However, if I'm trying to make the square root of negative 25, I can't, because there is no number that multiplied by itself equals 25. If I took 5 times 5, I'd get 25. If I took negative 5 times negative 5, I'd still get a positive, because negative times negative equals positive. So there's no way to multiply a number by itself to get back a negative. There are, however, some real-world situations that could really rely on us being able to find the square root of a negative. So that's why imaginary numbers were created. I is called the imaginary number. It has the property that I equals the square root of negative 1. This allows us to find the square roots of some negative numbers. A natural result of this is that I squared then must equal negative 1, because if I were to square both sides, I'd get rid of the radical and I'd be left with I squared equals negative 1. This is a property we are certainly going to take advantage of in this lesson. So let's do some examples playing around with some imaginary numbers. The first problem is going to have us add two imaginary numbers. Now, imaginary number looks like this: 5 minus I. It has the real number part, a addition or subtraction sign, and then the imaginary part. All imaginary numbers look like this. Now, if b is 1, then you're not really going to see anything attached to the I, like we see in this situation. If a were 0, then you wouldn't have a real number part, and you would just see the I term. So right now we have an imaginary number here, and an imaginary number here, and we want to add them together and see what new imaginary number we get. This is as simple as combining like terms. The real number part and the real number part can be added together to give us 5 plus negative 3, or 2, plus, and then the imaginary part, negative I, and the imaginary part 4i can be put together to give us 3i. And this is our final answer. Now in this next problem below, we're going to do subtraction. The first thing we need to do when we're subtracting is get rid of the parentheses. So I'm going to distribute this little negative 1 to the second set of parentheses. This is going to give us 8 plus 2i plus 4 minus 6i. Now we can go back to what we were doing in the last problem and combining like terms. 8 and 4, the real parts, can go together to make 12, and 2i and negative 6i can go together to make a negative 4i, giving us a final answer of 12 minus 4i. This next problem has nothing in between the parentheses, and that means multiplication. So we are going to distribute 3 to the 4 to make a 12, 3 to the negative 2i to make a negative 6i, I to 4 to make positive 4i, and I to negative 2i to make a negative 2i squared. Now remember, I squared equals negative 1, so this is really a negative 1. An order of operations now would say that I should take this negative 2 times negative 1 and multiply them together before doing any of the adding or subtracting. And a negative 2 times a negative 1 gives us a positive 2. And now we're back to the stage where we can combine like terms. 12 and 2 make 14, and negative 6i and positive 4i make a negative 2i. And that would be our final answer. Make sure that I squared is never in your final answer because it can become negative 1. In this last problem, we've got a square. So what we're going to do is we're going to write this out twice. You cannot just distribute the exponent. That won't work. And now this problem is going to look just like the problem we did before. Distribute, then replace that I squared, and then simplify, and finally combine like terms, giving us a final answer of 32 minus 24i. Now the next skill we're going to need to do is called rationalizing a complex denominator. The issue is we're not supposed to have i's in the denominator because I is really a square root, and we're not supposed to have square roots in the denominator. So there is a trick to get rid of an I that's in the denominator. What we do is we multiply the denominator by what's called the complex conjugate, which is the same expression but switching the sign in the middle. So instead of 4 minus 3i, we're going to multiply by 4 plus 3i. But if we do it to the bottom, we have to do it to the top as well to keep balance. Now we're going to have two multiplication problems. On top, we're going to start distributing, and then the other half. Same thing on bottom, and then finishing that off. And now before I go any further, something I want you to see is the middle of this bottom expression. You see how we have 12i minus 12i? That's going to guarantee that those two I terms cancel each other out and are out of the problem. That was by design. By multiplying by the complex conjugate, we guaranteed that this would happen. Now you might notice there's still an I in the denominator, but it's really an I squared, which is going to become a -1, so there's not going to be any i's left in the denominator. So we're going to rewrite this fraction, but get rid of the I squareds. So there we go, we've replaced the I squareds with -1, and now we'll simplify. Finally, we'll combine like terms, which on the top gives us -1 plus 18i, and in the denominator we'll see 16 and 9 make 25, and then the two I terms will cancel each other out because -12i and +12i equals 0. So if I just clean this up a little bit, here's our final answer. No more I in the denominator. Next, we're going to learn how to graph a complex number using what's called a vector. When we're graphing a complex number, what we normally call the x-axis is now going to be the real axis, which is going to be used for the real part of your complex number. The y-axis is now called the imaginary axis, which will be used for the imaginary half of your number. So 6 plus 4i would mean you should be at 6 on the x-axis, or the real axis, and 4 on the imaginary axis. That gives us a point right here. Now, a vector is a directional line segment that starts at the origin and points to that point that we just drew. And in our projects, we'll be using the vector representation of an imaginary number to solve some real-world problems. Now, there's also another way to graph a vector that uses the length of the line segment and the angle that it's directed. Something to keep in mind, the angle starts on the positive x-axis and rotates counterclockwise. We're going to be using this form of a vector, which is called geometric form, where the last form we showed was rectangular form, and it tells you the length and the angle. So if we're making a rough sketch of this, we would start on the positive x-axis, rotate 60 degrees. Now remember, this is 90 degrees, so we want to be a little more than halfway towards that, and then we're going to draw a directional line segment, which we know is 10 units long. And this would serve as a perfectly good sketch of this vector. Our last two tasks in this lesson are going to be converting from one form to the other. So starting with rectangular or complex form and converting into that geometric form that we just showed. So if we're converting, the first thing we're going to do is sketch this graph. We should be at 12 on the real axis and 2 on the imaginary axis. And this is what that vector would look like. Now for geometric form, we need to figure out how long is this line segment and what's the angle. Both of these questions can be answered with some of the trig that we learned earlier in the semester. If I draw a right triangle right here, I know that its height is 2. This distance from 0 to 2i, since I is basically -1, this distance is still 2. And we know this distance from 0 to 12 is definitely 12. We want to know this angle and this side. Well, by Pythagorean theorem, we can say c squared equals 12 squared plus 2 squared. So c squared equals 144 plus 4. C squared equals 148. So c equals the square root of 148, or approximately 12.17. And now for theta, we know that the opposite side is 2, and the adjacent side is 12. So we could use tangent and say that the tangent of theta equals 2 over 12. So theta equals the inverse tan of 2 over 12. Keep in mind we're in degree mode here, and we get 9.46. Now, geometric form is magnitude, then we use a less than symbol, and then we put angle. Well, c is our magnitude, so our geometric form is going to be 12.17, and then 9.46 is our angle. And this would be the geometric form of this vector. Finally, let's do this in the other direction. Again, we'll start by graphing. This 120 degree angle would be somewhere over here. It is important that we get the quadrant right, and we know this length is 20. If we complete the right triangle, what we're going to be trying to figure out is this x coordinate and this y coordinate. Now, if this was 120 degrees of rotation, that means that this is 60 degrees. And that information will be useful for us as we're at this point trying to solve this right triangle. Now, to find x, I know this angle, x is the adjacent side, and 20 is the hypotenuse. So I could use cosine. The cosine of 60 degrees equals the adjacent x over the hypotenuse 20. This gives us x equals 20 cosine 60, which my calculator tells me is 10. Now, as we try to solve for y, we still know that 60-degree angle, 20 is still the hypotenuse, and the y is the opposite side. So opposite and hypotenuse would say we could use sine. The sine of 60 degrees would equal the opposite y over the hypotenuse 20. So y equals 20 sine 60, which my calculator tells me is 17.32. Now remember I talked about it was important paying attention to what quadrant you're in. Notice that this x-coordinate should be negative because it's on the left side of the origin. So we found the length to be 10, but really it's a negative 10. So when we're writing this in rectangular form, we have negative 10, and the y-coordinate is positive. It's above the origin. So that's going to be a positive 17.32. So plus 17.32 I. Now we have rectangular form. Just a few things to remember as we wrap up this lesson. One is that I squared equals negative 1. The next is that rectangular form is a plus bi. And finally, geometric form goes magnitude, then the less than symbol, and then angle. If you came away with anything else, write it down now. Otherwise, see you next time.